Hi, my name is Brianna Poon, and this is my lab report for Lab 4, Magnetic Braking with Faraday's Law. So the purpose of this lab was to observe the effect of Faraday's Law on a powerful bar magnet that is dropped down a conductive tube of aluminum foil. And so the fundamental principles that I used in this lab were the Biot-Savart law, which is the magnetic field of a moving point charge, Faraday and Lenz's law, which combined says that the mth is equal to the negative time derivative of magnetic flux, where magnetic flux is the derivative of, the integral of the magnetic field dot n hat dA, and also Newton's second law, where force is equal to mass times acceleration, and Newton's third law of reciprocity. So the procedure here was to first drop the magnet through a tube of aluminum foil a couple times and calculate the time it takes for the magnet to fall through the entire length of the tube. And then I created a computational model of the experiment to calculate the theoretical time it should take for the magnet to fall. And then I compared my observed and predicted data. So my model here is illustrated by this picture here. The system is the magnet and the surroundings are the aluminum foil tube and the earth. And so also I have some initial conditions here where I have the dimensions of the aluminum foil tube and also the mass of the magnet and the magnetic dipole of the magnet that I calculated from lab 3, I think it was. And so here is my actual experimental data. So I calculated this by recording me dropping the magnet through the aluminum foil tube 5 times, and then averaging the time it took for the magnet to fall through the tube. And so next I wrote my glow script code. Since the whole thing was pretty long, I just cut out some of the most important parts. This first part here is where I created a function to calculate the magnetic field, and then another function to calculate the magnetic flux. And then this third part here is where I computed the magnetic field at each ring, and then I used Newton's second law to update velocity and position. And so here is what my computational model actually looks like. On the left here, this gray thing is the aluminum foil tube, and then the magnet is the blue and red thing here. And here is the velocity versus time graph. And according to my computational model, the time it took for the magnet to fall through is 1.021 seconds. So the intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current and which counterclockwise. So I know that red corresponds to the counterclockwise direction and blue is clockwise because together this combination results in the slowing down of the speed of the falling magnet. And so what happens to the dynamics of the system if you flip the magnet around? The magnet would still pretty much do the same thing. It would still slow down as it falls because like the magnet poles would be flipped, but so would the generated currents. So how does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be more accurate? My real-world time is faster than the computational time, which may have just been due to some experimental error. To make the computational system more accurate, I could include other forces like drag force. So what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? So it tells me that initially the gravitational force dominates, but the induced magnetic force eventually counteracts that and slows down the magnet a little bit. So my experimental time was 0.69 seconds and the computational model time was 1.021 seconds. And so there's obviously some discrepancy here, which may have been due to inaccurate measurement of time because of camera issues, because once again, I had to record the video of me dropping the magnet through the tube. And also the magnet made contact with the tube as it fell, which could have affected some of the results that I got. And also I could have tried to measure the tube a little bit more accurately. So what if the resistivity of the conductor were reduced as close as possible to zero? If that were the case, the magnetic force that is opposing gravity would increase, and that would eventually result in the balancing of forces and a net force of zero. So if holes or slots were cut into the tube, this would have the opposite effect. The holes would disrupt the flow of current through the rings and therefore reduce the magnitude of magnetic force and allow the magnet to fall faster. That's all I have for you today, and thanks for listening.